So far in our discussion of power functions, we've looked at U-shaped graphs, we've looked at S-shaped graphs, we've looked at butterfly graphs, and we've looked at volcano graphs. There are two other types of graphs that we're going to look at, and those are what I would call your radical graphs. Most familiar graph that we have so far is the square root graph. So we're going to be looking at square root, cube root, fourth root, fifth root, sixth root, and so on. And these are called rational exponents. These are exponents that are written as fractions of lowest terms or simplest form. Coming back to the form that we're fitting all of these power models in, they've got to look like this. F of x equals a times x to the n. I didn't mention it before, but I want to bring out some highlights here. A and n have to be non-zero real numbers. So they can be any number except 0. So we're saying that these values can be very varied and widespread. So far I've looked at when n was equal to a 2, 4, or 6. Well, that was an even power, so anytime that n was an even power, we had a U-shaped graph. We had n equals 3, 5, 7. Those were our S-shaped graphs. And then we experimented what happened when n became negative, so like -2, -4, -6. Well, those graphs were our volcano graphs. And then we looked at what happened when they were negative odd, so -3, -5, -7. Those were our butterfly graphs. So, like I said, I tried to recap this. We've looked at U-shaped graphs when the power was positive and even. They were S-shaped graphs when the power was positive and odd. If they were negative and even, it was a volcano graph. If they were negative and odd, then they were our butterfly graph. So now what happens when we look at when they're non-integer exponents? So that's what this discussion is about. They call them rational exponents, and it's still part of our power functions model. We're going to go like we've been doing. We're going to take a look at some parent functions and then deviate from there a bit. So we're going to go back into this drive program, and we're going to take a look at just what I call the parent function graph. I don't want you to get too uptight about this. The way I'm writing it, this is x raised to the 1/2, so it fits in that power model. If we remember what this bottom number means in our rational exponent, it means that this can be rewritten as the square root of x. That bottom number is always your index. So this one, where it says x to the 1/4, this could be written as y equals the fourth root of x. Bottom number is your index, the top number right now all we're considering is 1, but we'll see what happens with that. And so our final one would be y equals the sixth root of x. So we're going to take a look at the variations, what happens as we look and graph these three on the same axis. So that's the first thing, just to get a feel for what their shape is, because each of these have their own shape and feel. So we're going to graph y equals 1/2 x. That should be this graph if I've organized that correctly. So I got to go back and highlight it so it will graph it. But if I graph that on that grid, it should just erase or go right over the top of that line, because that's the way I had it designed. So that is y equals the square root of x. That's x raised to the 1/2. So we're going to stay with the even numbers. Instead of square root of x, we're going to go the fourth root of x, or x to the 1/4. If we graph this one, we're going to see some noticeable changes. Okay, so the one point that's always an anchor point, still has been, is still the ordered pair 1, 1. I don't care if you take the square root of 1 or if you take the fourth root of 1, you still get a 1. It doesn't matter what root you take, actually, you're always going to get a 1. So 1 will always be a point in common. So then what's going on with this beyond 1? We've always examined what's happening between 0 and 1, and now we're going to look at what happens after 1. Well, between 0 and 1, you notice our graph is higher, so it's going above our original graph, x squared. That means that we're taking the fourth roots of fractions. Now, a nice number to pick out of this one would probably 1/16, just because we can do this fairly quickly. If we take the square root of 1/16, the square root would be 1/4. Where if we compare that to taking the same input value of 1/16 and taking the fourth root of 1/16, that is 1/2. So that half is higher than our 1/4. So we see that it's going to be higher or above our other graph, our x or square root graph. As we go out on the outsides, then just the opposite is happening. We'll take a number. It's really hard to get out there that far because of the fourth root, but I'll just have to use 16 because it's the easiest one to use. So What if we take the square root of 16? We would get 4. Or if we took the fourth root of 16, we would get a 2. And you can see that this is on the path to be higher out here. Once we get to 16, it's going to be at a 4, where on our fourth root graph, it's only going to be at a height of 2. So it's coming in for 16 at 2, where on the square root, it was at 4. So that's the nature of the graph that we're looking at. So we're going to compare it to one other one, and that other graph I want to take a look at is what happens when we go y to the 1/6. Okay, so if we reason the way that we had before, we should see that inside this, between 0 and 1, this sixth root graph should be a little bit higher, should come above that, should still cross through 1, not a very good picture of that, and then it's going to be below on the outside. So let me clear that out and we'll let it graph it. Okay, and just to get a little different color in there, a little easier to see, we can see that as this power gets bigger and bigger, as we go from the second root to the fourth root to the sixth root, in between 0 and 1, we're going to see these values get a little bit higher and higher, but as we get outside, then our graph is going to flatten even more, so the rate of change lowers. So that's what that function family looks like. Probably better make note of this. There is no other part of this graph. As you can see, I got this shifted over so we could see it well. But we've already done this several times. We can't take the square root of negative. So if we do the square root, we've always put a limitation where x has to be greater than or equal to 0. That's going to be the case for any even root, no matter what. We want to make sure that the stuff underneath here has to be greater than or equal to 0. Otherwise, it'll be a non-real solution. So anything on this side of the graph, anything left of 0, does not have a real function or a real value output that we can graph and mark on our real number line. So this is it. That's all you get from these. You get, that's just a part of a graph. And you'll see what I'm talking about in just a minute. The other ones that we're responsible for are not just square root, fourth root, sixth root, but cube root, and the fifth root, and the seventh root. So now we're looking at odd rationals, in a sense. I'm going to graph this on a graphing calculator, and then I'm going to graph it on this program. When you do this on your graphing calculator, you shouldn't have any trouble with it whatsoever. I'm having a little bit of trouble with this graphing program on my computer, but x to the 1/3. Here's a little bit different shift. We haven't had much of this, but let me show you the graph first, and then we'll discuss why it has more values on it. So I got to select it. I want to make sure that I graph it. As you can see on this cube root, not only are we getting things up here in the first quadrant, but we're also getting things down here in the third quadrant. Okay. Now we never really have a problem when we take the cube root or an odd root of a negative number. If we think through this problem, what is the cube root of a negative 1? We're saying, what number could I multiply times itself 3 times and end up with a negative 1? Well, that is a negative 1 times a negative 1 times a negative, negative 1. I was thinking of my next example there. Okay. The next one would be like the cube root of a negative 8. That's the next easy one to do, because it would be a negative 2 times a negative 2 times a negative 2. So contrary to what we've been doing with all the other radicals, because we've only been focused on even roots, now when we do odd radical powers, now we got to worry about the other part of the graph, which is possible. It's okay to go out here and put in a negative 8. 1, 2, 3, 4, 5, 6, 7, 8. It should come back in a negative 2. And that's what it's showing you there. So these give you the second part of the graph that you haven't been getting before. So I'm going to clear that off. I'm going to put this calculator away. Or the other thing that we could do quickly is just look at the table of values. We'll start it at 0, and we'll go to an auto. And we'll go to our table of values. And you can see that in this table of values, you get both positive and negative outputs. And if I go down to 8, that's where we're going to see the 2. If I go up here to a negative 8, and negative 1 is a negative 1. If I go to a negative 8, there's 2. The next easy one we're going to get to is 27, because the cube root of a negative 27 is going to be 3. So you can see the rate of change is really slow as we go outside of 1 and negative 1. But even on these, we'd have to break that interval down a little bit. You can see the higher rates of growth on the calculator. So I want to clear off this, and I want to show you these other graphs. So this graph is the same graph you were looking at on the calculator. It is the cube root of x. As I said, I'm having a little bit of difficulty with this graphing program on the calculator. I haven't quite figured this out, but what I did end up figuring out is how to graph them, but I had to put them in as two equations. So I have to put them in like this to show you what the graph of the fifth root of x. Okay. Again, we're seeing the same information, same thing that we're doing. All we're doing is we're seeing this rotation around the origin. So if we rotate 180 degrees, we're getting the second part of the graph. The purple was our parent graph, and we can see from 0 to 1, the black graph, or the new graph we just did, which was the fifth root, is coming up a little bit higher in between 0 and 1, and then it's flatter outside of 1 to infinity. So flat on the inside, or rapid rate of growth on the inside, a little higher, flatter on the outside. So then I'm going to graph one more just to show you the last pattern. I've always given you 3, and here's the third one I'm going to give you. This is y equals x to the 1/7. That means we got the 7th root of x. You can see it comes up a little bit higher on the insides, and the outside it's a little flatter. And then when we look at, like I said, you should only have to put in that equation, the first equation that I graphed, but in order to get to graph the whole thing on my computer, I've got to do it twice. So there's your graph. It's an S-shaped graph again. It's turned sideways. So we got these two patterns. Our even roots are only in the first quadrant. Our odd roots are in the first and the third quadrant because we can do the negatives. So quick glance at those graphs. So okay, got a couple more things to talk about, and then we can go ahead and get started with this. When you have a number, such as, I'm just going to break this other one, 2 times x to the 3/4, one of the rules that you can use with these rational exponents, we already know that the bottom number is your root. So forget about the 2 just for a second. I'm just going to concentrate on this x to the 3/4. The x to the 3/4 can be written in an equivalent form as the 4th root. The bottom number is always your index times x to the 3rd. And that's really what this rational exponent is doing. And they're describing that up in here. Where x to the p over n, where if we put that, it's really the x to the p to the nth root of it. So the nth root of x to the p, that's the explanation they're doing here. I just gave you a concrete example of what it looks like here. The bottom number is your index. The top number is what you're doing to the inside of that radical. So we're cubing. Okay, so let's begin the discussion on the function that they give us. Our function is 2 times x to the 3/4 power. Again, if you wanted to, you could rewrite this as this is 2 times the 4th root of x to the 3rd, and that might be helpful when we start looking at our domain and continuity and other tests that we're going to look at. The first thing I want to do is I wanted to show you a graph of y equals the 4th root of x, or again, just keeping in mind, just trying to get used to this notation, is x to the 1/4. That's what it looks like. Here it is in the green. Now when we compare that to our other graph down here, or looks a little bit more in blue, we see the common point is 0, 0. We also should see the common point of, well, our order pair 1, 1. I'm not going to call it common because there's going to be some adjustments to that because we're doing a vertical stretch, and we also got a cubed in there. So general sense of what I want to get you to have a feel of, since we multiply by 2, you can see that the vertical stretching is taking place. It's not as flat in here. It's gotten stretched out, and it gets a little bit higher rate of change out here, which means we're doubling all the outputs of our 4th root of x. And the other thing that we did is we took x to the 3rd. At this point, we're not going to be held too accountable for knowing what's going on with that, but just take a look at this simple point, the order pair 1, 1 again. If we take the cube root, if we take the 4th root of x to the 3rd and multiply it by 2, and we're using an input of 1, that means we're going to take 2 times the 4th root of 1 cubed. 1 cubed is 1, and we're going to take 2 times the 4th root of 1. The 4th root of 1 is 1, so that means we're going to take 2 times 1, and we just get 2. So we see the vertical stretch here. We got an input of 1, and it gives us an output of 2. So fitting that back into our transformations, we struggle with that a little bit in that first unit. We got to keep trying to press that and make sure that we're getting our transformations figured out. The domain and range. Okay, so right away, one of the big keys here is that we've got a 4th root. Anytime it's an even root, We are an automatic alert. We can never let the stuff underneath the radical be negative. So that right away tells me that x has to be greater than or equal to 0. So our domain is simply x is greater or equal to 0, or if we want to put it in our interval notation, this goes from 0. Oh, I better use a square bracket because we can have a square root of 0, or in this case a fourth root of 0, 0 to infinity. Our range. Now our range are limited to the outputs that it can only be positive. Or we can't get any negatives out of a radical there because we can't take the square root or an even root in this case, fourth root. Can't get any negatives. So our range is going to be all real numbers that are greater than or equal to 0. So again, it's going from 0 to infinity. So we got our domain and range taken care of. Intercepts. There's one place where this crosses the x and the y-axis, so our x and y-intercept is at the origin at order pair 0, 0. End behavior, we want to describe that end behavior. So we're going to look as x approaches a positive infinity. There's nothing on this side of the graph over here. So as x approaches a positive infinity, y is approaching a positive infinity as well. Continuity, our graph is only continuous from the origin all the way out to infinity. So when we talk about continuity, we want to list it from, got to include 0, 0 to infinity. From this point on, this graph is continuous, doesn't have any breaks or gaps in it, but can't go to the other side. And where is the function increasing or where is it decreasing? As we read this graph from left to right, this graph is continually increasing. So it's decreasing nowhere. And where is it increasing? It's increasing on the entire interval from 0 to infinity. Okay, so that is our fourth root graph with some modifications together. Second example is basically a cube root function. The reason I know it's a cube root function, I look at the base, or the bottom of that fraction. So it's really 10 times the cube root of x to the fifth. So what I wanted you to do is, again, pay attention to what is the cube root of x graph look like. So I put its parent function right here. This is our cube root graph. Remember, the difference on these is that we're going to pick up not only in the first quadrant, but we also get those in the second or in the third quadrant because we can take the cube root or even an odd root of any number, positive or negative. So that's going to change some of our answers in here. So what's going to happen when we multiply it times 10? That's going to take all of these outputs of the cube root of x. Didn't do a very good job there. Let's try it again. Take all of the cube root of x outputs, and then we got to take them down here, and for sure multiply them by 10. So what I want to pay particular attention to is the stretching by multiplying by 10. So again, we're going to track our point of 1, 1. The order pair 1, 1 should now become stretched when we put a 1 in for x, x to the fifth. 1 to the fifth is 5. The cube root of 1 is 1. So 1 times 10 is 10. So this graph is going to be really hard to tell. So you're going to zoom off there. This is going to and will eventually hit 10. So we got our vertical stretch. I didn't do a very good job of getting my scaling in there so you can see that, but it should be enough. This is the graph that we're going to be looking at. For you guys, what you're going to do is you're going to type that in your calculator. You're going to take a look at your graph. You should already know going in what the graph looks like, and that's the important part of this discussion. We know we're going to have either this half of a graph for our even roots, and then the full graph if it's an odd one. They want us to list the domain and range, so let's talk about this graph's domain and range. The domain, I want to look from left to right and see if there's any gaps in it. Just contrary to the other one, there wasn't anything over here, so we knew that we had some limitations. But on this one, we got a continuous curve that's coming from negative infinity and looks like it's continuous all the way through positive infinity. So our domain on this is from negative infinity to positive infinity. Our range is going to go from, looking on your y-axis, up and down, no gaps, no breaks. So it's going from negative infinity to positive infinity as well. X-intercepts and y-intercepts, they have a common point. It's where it crosses the x-axis and the y-axis at the origin. So x and y-intercepts begin or at the origin, 0, 0. End behavior, we'll discuss this. As x approaches the negative infinity, the y values have to be approaching. Since it's going downhill, as x's go to the left, y is approaching a negative infinity. The other one, as x approaches a positive infinity, so as we let x go towards positive infinity, the y's are going up. So y approaches a positive infinity. So we've just described the end behavior. Continuity, contrary to our even roots, this function is continuous everywhere. Before, when we did our even root, it was continuous only in the first quadrant, but this one's continuous in first and third. It's continuous everywhere. So continuity, we're going to go from a negative infinity to positive infinity. It's continuous on the entire ring, entire domain. And finally, where is the function increasing? Where is it decreasing? This is a nice, easy graph to do because of the way, the nature of the graph. As we go from left to right, it's always going uphill. It's continuously going up. So it's increasing on the entire interval from a negative infinity to infinity. It's decreasing nowhere or never. Okay, so now we've looked at two other types of power, at least two other shapes of power models. Our square root that we've been familiar with, and now we're going to make you more responsible for cube roots and odd roots, and that's the other part in the third quadrant. So that concludes our discussion of power models. The next part will be on radical functions. So at this point we can stop, and we'll call this good for our first objective, and that is making sure that we can handle these power functions. So a lot of diversity here, a lot of things to remember. Broke it down in 3 different segments for you.